Hello everyone, welcome to this advanced course on heat transfer modeling. In this particular course, we will see advanced topics or modules within the heat transfer modeling section of ANSYS Fluent. How do we model complex heat transfer problems? What are the options or different models available within ANSYS Fluent in order to take care of different heat transfer phenomena? We will see all these in this particular course. This is the first lecture of this course, and here we will have an introduction to heat transfer. As such, we will cover all the basics or review all the basics of heat transfer, fundamentals, fundamental concepts, and all the theory and what all we need in order to approach a heat transfer simulation problem. So let us begin our lecture here. First, we will have an overview of the content of this particular lecture. Initially, we will have an introduction to the topic of heat transfer. We will see why we need to study heat transfer. Different modes of heat transfer will be discussed. Then we will go into detail the fundamental concepts of conduction, convection, and radiation phenomenon. After that, we will see fundamental concepts or theories of heat transfer. We will discuss some important dimensionless numbers related to heat transfer and what is their use, and we will end this lecture with summary. All this fundamental knowledge that we discuss in this particular lecture will be very useful in order to tackle a CFD problem related to heat transfer. So this particular review lecture or a base lecture is very important in order to go into CFD or computational heat transfer. We will not discuss anything related to software in this particular lecture. This is just a review or a basic lecture which will cover fundamentals of heat transfer. So when we say heat transfer, what do we mean by heat or heat energy? Now basically heat is a form of energy that can be transferred from one system to another because of the temperature difference between the two systems. An example from daily life is a hot cup of coffee which is at a high temperature and it is giving away heat to the environment which is at much cooler temperature. Now this phenomenon of transfer of this particular energy is called as heat transfer. And this is a science which deals with determination of rates of such energy transfer. The rates by which this transfer of energy occurs is extremely important in commercial or industrial systems. So heat transfer is a science which deals with the rates of such energy transfers which occur due to the temperature gradient or temperature difference between two systems. You can see the example here, a slab, one side of which is exposed to 30 degrees centigrade and the other is exposed to 20 degrees centigrade, and we have a temperature gradient within the thickness of the slab, and because of this temperature gradient there is a heat flux or heat energy transfer rate which is associated through this slab. So heat energy is getting transferred here, and this rate by which heat energy is getting transferred through this thickness is extremely important and is the topic of study within heat transfer. Now we have to note that the basic requirement of heat transfer or the basic requirement for heat transfer to occur is the presence of temperature difference. So why do we study heat transfer and why is this science so important? Now this is a very commonly encountered phenomenon in engineering and real systems. Everywhere you go there is heat transfer. We observe it in our daily life, whether we have a cup of coffee or whether we prepare our food or whether we survive in the external environment. Our body is also undergoing heat transfer. We also encounter in industry in sections like power plants, nuclear plants, automobile industry, combustion engines. So heat transfer as a phenomenon is present everywhere. It is a commonly observed phenomenon for many things to survive and function. So as I just said, human body is also constantly rejecting heat to its surrounding, and human comfort is closely tied with the rate of heat rejection. So heat transfer basically starts from our own body. We try to control this heat transfer rate by adjusting our clothing and environmental conditions. The human body needs to, in order to survive, it needs some appropriate temperature, and in order to maintain that temperature, our body constantly is interacting in the form of heat energy with the surrounding. Some of the commercial or commonly observed real-life examples where heat transfer occurs is examples like this electronic component PCB or electronic component board. This is a heat exchanger, a power plant, a refrigerator, an air conditioning system. So all these devices like heating and air conditioning system, refrigerator, freezers, water heater, the iron, even computers and electronics equipment, car radiators, solar collectors, so various components of power plants and even spacecraft. So wherever we go, we observe heat transfer in industry as well as in real life. So this is an extremely important phenomenon that needs to be studied in order to design or analyze anything, whether it is small clothes or whether it is bigger products like power plants and spacecraft. So we need to take care of the heat transfer and need to design products so that appropriate amount of heat transfer functioning is obtained or is maintained. So as I just said, there are different modes of heat transfer. Now you must have encountered such grills either in your food preparation or any of your kitchen equipments. So this is a form of a grill used for barbecue, etc. Now what do we observe here is the lower side there is basically fire which is heating up the grill parts. So all these grill parts are basically getting heated by this fire that is below here, that is burning. So this grill part, once it gets heat from this particular fire, the heat transfer that is occurring in between these grill parts, that is if this particular part is getting heated, because of this grill part, this side of the grill is also getting heated, and that internal heat transfer is because of conduction. Within the grill, the heat is transferred by conduction. In your daily life, how many times it has occurred that your CPU fan is making enormous amount of noise and your CPU is just getting heated up? This is an extreme example. In order to cool the CPU, you actually get a table fan and put it beside the CPU because your CPU is not able to handle the heat. So now this fan throws air in order to cool the CPU, and this particular phenomenon by which the CPU is getting cooled is called convection. So this is a very funny or sort of a very extreme, desperate example of convection where you are trying to cool your CPU cabinet by a table fan. So now a very common example of heat transfer that is needed in order to survive life on Earth is light radiated by sun. So sun is radiating light, and that light contains some amount of heat that is in the form of radiation. So sun is giving away sunlight and that is a form of radiation heat transfer to everything on Earth. This is an example of radiation in nature. We will see fundamental concepts and theory behind conduction phenomenon. Now when we say conduction, in that heat moves through material due to molecular action only. So the primary mode is molecular action in order for conduction to occur. In solids, this molecular action is in the form of lattice vibration and flow of free electrons, whereas in liquids it is in the form of molecular collision and molecular diffusion. In gases, which are still rarer in terms of density, it is again in the form of molecular collision and molecular diffusion. Now when we say conduction, there is a law which governs conduction phenomenon, which is referred to as Fourier's law. Fourier's law states that the heat flux due to conduction is proportional to the temperature gradient, which means that the heat that is transferred, the heat flux, that is the heat energy rate divided by the area, that particular heat flux is proportional to the temperature difference or temperature gradient across that distance. So what we say is Q by A, which is given as a heat flux, is equal to some proportionality constant into the temperature multiplied by the temperature gradient. So if we are about to find heat transfer rate, it will be given by K, that is proportionality constant, into area into the temperature gradient, that is dt by dx, which can be written as K multiplied by area multiplied by temperature of one side minus temperature of second side divided by the thickness or the distance between the two sides or 2 points. So this is how the heat flux or the Fourier law states how heat flux is calculated. As you can see, this is the distance in x, and this is the hot side, this is the cold side, and this is how the temperature profile will look like. And this temperature profile, because of conduction, is governed by Fourier's law or is described by Fourier's law. This is again a linear proportionality, or you can say this is a straight line in this particular case.